Hello, this is Dr. London, and today we're going to talk about global extrema, actually. Last time we talked about local extrema. So, global extrema, meaning sometimes also referred to as absolute extrema, means, global maxes and mins. So that means they are the absolute largest for a function over its entire domain, or the absolute smallest y value for a function over its entire domain. So let's highlight the difference by looking at just kind of the simple picture. So I've indicated 6 points here. So this is a function that basically starts at point A and ends at point F. There are 3 local maxes, meaning the largest values that you see in some small area. So those are going to be points A, C, and E. And we also have 3 global mins that occur. So we see those are points B, D, and F. Now those are local, meaning they look like either the top of a small hill or the bottom of a small valley, but they aren't the absolute. For instance, D is a local min, but by far it's not the smallest y value you see on the graph. So that's what the global values are. So if we talk about the global max for this function, or sometimes it's referred to as the absolute max, it's just the single point C. That's the highest y value you see on the entire graph. And the global min actually occurs at an endpoint. It occurs at the point all the way to the right of the function, which is f. So we'll learn in the extreme value theorem, so that's what we're going to use. That's going to allow us to look at the formula of a function and use the derivative to figure out what the global max of a function is and what the global min of a function is. And it's actually a little bit easier in terms of using the formula to find these things than it was for maxes and mins. Because for local maxes and mins, what did we have to do? We had to take the derivative, set it equal to 0, and then use test value regions. So with the global ones, we're going to still have to take the derivative, set it equal to 0, but then what we do is we actually just test the critical points and the endpoints. So there's no need to set up these test value regions and do all that business like we did for the first derivative test. So the test that we're going to be using here is known as the extreme value theorem. So the extreme value theorem, which sometimes we'll abbreviate EVT. So there's 2 hypotheses that are required in order to apply this theorem. So it says basically your function has to be continuous and it has to be on a closed interval. So a continuous function on a closed interval will attain both a global max and a global min. Moreover, these will occur at either critical points or endpoints. So let's look at some examples. On how to apply this. So let's just summarize the strategy first. So the strategy for applying this theorem is 1, take the derivative, 2, set to 0 and solve, 3, compare y values for critical points and endpoints when plugged into the original function. So we're not plugging them into the derivative. I see that mistake quite frequently. We're plugging them into the original function because we're using the derivative just to find where the critical values are, and then we're comparing all the y values in the original function. So let's start with a couple polynomial examples. They're typically the easiest. They have the most regular behaving derivatives. So identify all global extrema. For, let's say, f of x equals x cubed minus 3x squared, and our interval is -1, 2, 3. So taking the derivative is easy. We just apply the power rule here. So f prime of x is 3x squared minus 6x. So we set that equal to 0, and we can solve by factoring. So we can factor out a 3x, and that's 3x times the quantity x minus 2. So our two critical values we get are x equals 0 or x equals positive 2. So we have four things that we need to plug into the original function f. We have the endpoints -1 and 3. And we also have the two critical values, 0 and 2. So basically what we're doing is we're doing f of -1, f of 0, f of 2, and f of 3. And we're plugging each one of those things into f of x. Actually, they all come out exactly, I'm pretty sure here, so I don't need squiggly equals. These are in fact exactly equal to. So if you plug -1 into f of x, you get a y value of -4. If you plug in 0, you get 0. If you plug in 2, you also get -4. And if you plug in 3, you get 0 once again. So all four of these points turn out to either be a global max or a global min. If they occur at the same exact y value, then they're going to be both. So basically this point right here is a global min because it's the smallest y value. This one is a global max because it's the largest y value, which makes a global min at x equals 2 and a global max also occurring at x equals 3. So pretty straightforward there. Derivative was easy. Resulting equation was easy to solve, and we end up identifying all of our global extrema. So let's look at one more polynomial example. So maybe we'll call this first example just example A, because the instructions will be the same for subsequent examples. We're just trying to find the global extrema in this section. So B, let's now look at f of x equals 2x cubed minus 9x squared plus 12x plus 1 on the interval -0.5 up to 3. Okay, so again, we need to take the derivative. Again, this is a pretty easy derivative. We're just applying the power rule over and over again. So we'll end up with 6x squared minus 18x plus 12. Set that equal to 0. And if you notice, all three numbers are divisible by 6. So we can start by factoring out a 6 to make factoring a bit easier. So we get 6 times x squared minus 3x plus 2, and then that resulting polynomial will factor into x minus 2 times x minus 1. So we get 6 times the quantity x minus 2 times x minus 1. So the two critical values we see here are x equals 2 or x equals 1. So again, we have four numbers to plug in. The endpoints -0.5 and 3, and the critical values 1 and 2. So we want to do f of -0.5, f of 1, f of 2, and f of 3. And again, you just want to plug these things into your calculator, and we end up with negative 7.5 as our first y value. If we plug in 1, we should be getting 5. Sorry, I forgot about the plus 1, didn't I? Let's see. So 14, 15, minus 9 is 6. So yeah, I forgot about the plus 1 there. If we plug in 2, we get 5. And if we plug in 3, we get 10. So comparing the y values, the smallest y value is negative 7.5. So this would be our global min. And the largest y value is 10, so that would be the global max. And that's all there is to it on these problems. Nothing too tricky. Okay, let's look at one more polynomial example, then we'll look at a few that are a little bit different. So let's say we have now g of x equals x cubed minus 9x squared minus 48x plus 52. I believe we looked at this to identify local extrema, but now we're trying to find the absolute extrema on the interval negative 5 to 14. So again, we can take the derivative. So g prime of x here is just going to be 3x squared minus 18x minus 48. We can factor out a 3 and get x squared minus 6x minus 16. And then the remaining polynomial can be factored into x minus 8 times x plus 2. So the critical values that we generate are x equals 8 or x equals minus 2. So we again have 4 points to plug in. So g of negative 5, g of minus 2, g of 8, and g of 14. So one thing to keep in mind is really the x values don't give you any information about whether you have a global max or global min. So don't look at those when you're trying to determine anything about is it a max or is it a min. They don't really tell us anything except for where it's happening. We really only look at the y values. So when we plug these in, again, remember we're plugging into that original function g of x equals x cubed minus 9x squared minus 48x plus 52. We get minus 58. 104 minus 396 and 360. So our smallest y value is minus 396, so this would be a global min. And our largest is 360, which is a global max. So sometimes you'll see them ask, okay, where does the min occur, where does the max occur, and what are the values? So if a question is worded that way, we would say, okay, the global min occurs at x equals 8 and has value negative 396. And for the max, we would say the global max occurs at x equals 14 and has value 360. So let's look at examples with some other functions. These functions actually are on closed intervals, so we're actually going to have to use some test value regions to talk about their global extrema, but we'll comment on why they are in fact global extrema. But it's more of an ad hoc approach, and because they don't occur on a closed interval, we're technically not applying the extreme value theorem. So let's say find all global extrema for each function. So the first function is e to the 3x minus e to the 2x. So again, notice that there's not a specified domain. So still we want to take the derivative, set that equal to 0, and solve. So remember the derivative rule for continuous exponential functions. The derivative of e to some constant times x. If you take the derivative, that's just k e to the kx, where k is a constant and x is your variable. So the derivative here would end up 3e to the 3x minus 2e to the 2x. So we want to set that equal to 0 and solve. So we get 3e to the 3x minus 2e to the 2x. That's equal to 0. And add 2e to the 2x to both sides. We end up with 2e to the 2x equals 3e to the 3x. So what we want to do is, everything is being multiplied and divided here, so we want to move the exponential parts to one side and the regular numbers to the other side. So let's start by just dividing by 3. So we'll have 2e to the 2x over 3 is equal to e to the 3x. And then what we want to do is we just want to divide both sides by e to the 2x. So if we multiply it by, say, 1 over e to the 2x here and 1 over e to the 2x on the right-hand side, we will end up with just 2/3 on the left, because the e to the 2x's will cancel. And on the right, we'll have e to the 3x over e to the 2x, and you can subtract those exponents because you have the same base. So 3x minus 2x is x, so we end up with just 2/3 equals e to the x. And to solve for x, we just take the natural log of both sides. So the natural log of 2/3 is the natural log of e to the x, but the natural log and e to the x cancel, so we end up just with x equals the natural log of 2/3, which is about negative 0.41. So, since this function is continuous and its domain is just x values, all real numbers, then we just want to set up a test value region. So if we set up a test value region, we want to, well, we have that number right here, negative 0.41, and we just want to see, is the derivative positive or negative in each region? So pick some value, plug it into the derivative, so f prime of x, and see if you get a positive number or a negative number. So let's say we plugged 0 in. That would be on the right-hand side. So if you plug in 0, you would end up with the derivative value of 1, right? It would just end up with 3e to the 0 minus 2e to the 0, which is equal to 1. So we actually end up with a positive derivative on this side and a negative derivative on this side. So basically what that means is our function is decreasing until we get to negative 0.41 and then increasing thereafter. Basically that means a minimum is occurring at negative 0.41, and because the function decreases until it gets to negative 0.41 and then increases thereafter, we know that that value actually has to be a global minimum. So we can say a global min occurs at x equals negative 0.41 and has value. So to figure out the actual value of that global minimum, you need to plug it into the original function. So you need to plug it into f of x, not f prime of x. And if you do that, if you plug negative 0.41 in, you get a y value of about negative 0.15. So that would be the global minimum. Its coordinates would be about negative 0.41, and the y value would be about negative 0.15. Now let's just remember that we can always graph these things to try and help us confirm our results or double check if we're near a computer. So let's go ahead and do that. Let's go to Desmos. So desmos.com, nice graphing utility. So let's just graph our function f of x equals e to the 3x minus e to the 2x. And we see that we get a graph that has that little dip in it, and if we zoom in on the coordinates of that point, hopefully they confirm what we see. Yeah, we get about negative 0.41 and negative 0.15. So I rounded to 2 decimal places to 3 decimal places accuracy. It's about negative 0.405 and negative 0.148. So let's go ahead and look at another of these type of examples. So did I call that part A or anything? Yes, I did. So let's look at one more such function. So let's look at B. Let's say we have g of x is equal to x minus the natural log of x for x greater than 0. So the derivative function here, g prime of x, would be just 1 minus 1 over x. Very easy equation to solve. You would end up with 1 over x equals 1, and then you could just cross multiply. So we end up with 1 equals x. That's our only critical value for this function that has domain x values greater than 0. So again, we can't plug in 0, so our domain kind of looks like this. You can't plug in 0, but we see a critical value at 1. So we need to plug in some number between 0 and 1 and some number greater than 1 into g prime of x. So let's say we plug in 0.5. 1 minus 1 over 0.5 is 1 minus 2, so we get a negative g prime value in this region. And if you plug in something bigger, say 2, 1 minus a half would end up being a positive value. So again, we see the function decreases until you get the x value of 1 and then increases thereafter. So we would say a global min occurs at x equals 1 and has value g of 1. We have to plug it into the original function, so that would be 1 minus the natural log of 1, and the natural log of 1 is 0, so this y value is 1 as well. So that would be a global min there. Okay, so those are two example problems that they might ask for the global extrema, but in fact they are not on a closed interval, so you kind of have to use those test value regions, and usually with the domain in the test value regions you can infer that they are in fact global extrema as well. So let's go ahead and look at a word problem. So we'll look at a few more of these in a future section, but the same sort of thing occurs. So let's go ahead and look at this as a final example. So this is known as an optimization problem. Basically, it's an application of this technique to a word problem. So we have the product of two positive numbers is 784. So let's ask, what is the minimum value of their sum? So, we list the variables that we want to use to solve the problem. So let x and y be the positive numbers. So there's two things. We have the relationship. So we have the thing that we want to do. We want to minimize their sum. So minimize the sum, which we know is just x plus y. So that's known as the optimization function, because that's the thing you're either trying to figure out a max or min for. And then you have the constraint equation, which is how you relate the two variables so that we can get our multivariable equation down to a single variable. So the constraint here is that we know if we multiply them together, we get 784. And now what you want to do is you want to, like I said, replace one of the variables. So typically that means we want to solve for one of the variables, so we can use that constraint equation to replace that letter in the optimization function. So here I'm solving for y, so we end up with y equals 784 over x, and we can plug that back into the optimization function. So our sum, s, is now, instead of x plus y, it's going to be x plus 784 over x. And let me just write that as x plus 784 times x to the negative first power. So now this is what we want to take the derivative, set to 0, and solve. So if you do that, we end up with s prime equals 1, and then the negative 1 that comes down is going to make this minus 784, and when you subtract 1 from the exponent, we get x to the negative 2. So we set this to 0 and solve. So 1 minus 784 divided by x squared. So let's move that 784 over x squared to the other side. So 784 divided by x squared is equal to 1. Now we can cross multiply, so we get 784 equals x squared. Typically, you would solve this by saying x is plus or minus the square root of 784. But in this case, we do know that x and y had to be positive values, so we don't have to worry about the negative square root. So this is going to be the square root of x squared, if that helps you see that. So we get x is 28. So then we want to plug that back in, so we know y is 784 divided by x, which we now know is 28. So this is 784 over 28, which also comes out to 28. So both numbers, x and y, are 28. So we can say hence the minimum sum is 28 plus 28, which is 56. So that's how you would solve that word problem. It's not super interesting, this example, because the constraint is kind of basic, but we'll look at some more interesting optimization problems next time. A lot of times what happens is they relate to formulas from geometry or the Pythagorean theorem, something like that. Sometimes they'll give you an explicit function and a specific constraint. But these things popped up all the time. People are always interested, in especially in economics, maximizing profit or minimizing cost, things like that. So these optimization functions are and problems are definitely applicable to all sorts of real life scenarios. But anyway, that's it for Global Extrema. So I will talk to you soon. This is Dr. Lennon signing off.